Okay, so this unit is going to be bonding. So last time we talked about metals and nonmetals, right?
Yes.
We know there's lots of metals, there's not as many nonmetals. What do the metals like to do with their electrons? They give them away. Metals will always give their electrons away. What do nonmetals do? They take, but they can also share, okay? And so they can actually participate in two different kinds of bonds, okay? So a chemical bond, and the words that you need to fill in your blanks are going to be underlined in red, okay? A chemical bond is the mutual electrical attraction between the nuclei and the valence electrons. Remember we said last time valence electrons are the electrons that are available to be lost, gained, or shared when they form compounds, okay? The chemical bond is a strong, attractive bond between atoms or ions in a compound, okay? And there's going to be three basic kinds. The reason that bonds form is, first of all, they want to minimize their potential energy. Okay, nature likes things in the lowest possible form of potential energy that it can get, and so it bonds to do that. So that in terms increases its stability. For instance, we said group 1, the alkali metals are very reactive, and you can't find them free in nature because they are not stable with just their one valence electron. So they bond and they become more stable. So that's one of the reasons why they bond. So the three types of bonds that we're going to talk about, this is not in your notes, it's just an overview so you know what's coming, is an ionic bond, which occurs between a metal and a nonmetal in most cases, a covalent bond, which is two nonmetals, and then a metallic bonding, which is between two metals. Okay? So the first one is ionic, and it is the chemical bond that's from the electrical attraction between the cations and the anions. Okay? It has an electronegativity difference of greater than 1.7. Greater than 1.7. And in this case, the electrons are outright transferred. Okay, and they're not sharing them. They're outright giving and taking. Okay. We recognize the fact that it occurs most of the time between a metal and a nonmetal. Okay, between a metal and a nonmetal. Some examples that you would be familiar with are good old table salt, NaCl. That would be an example. It's a metal and a nonmetal. Copper 2 sulfate, which you don't know how to name yet, but you will, would be another example. That's a metal and a polyatomic ion. And then potassium bromide would be another one. Okay. Remember when we did the flame test and we burned the colors and we made pretty fire? All of those chemicals that we did were ionic salts or ionic compounds. They were all metals and a nonmetal. We just dissolved them in water, and that's why they were able to do that. Okay, the metals are what gave the color to the flame. The nonmetal didn't do anything; it just hung out and watched. Okay, covalent bonding is the sharing of electrons between two atoms. Okay, we recognize the fact that they occur between two nonmetals. So some very good examples of covalent bonding is something that you have to have every day, or you would die. Water, H2O, is a covalent bond. Someone said oxygen. That is correct as well. And remember, it's one of our Brinkelhoffs that we have to know is a diatomic molecule. So O2 is a covalent bond. Okay. And then how about, just to make life sweeter, table sugar? That would also be a type of covalent bond. That is sucrose. That's table sugar, not glucose, which is part of cellular respiration. Okay. So this is what a covalent bond would look like in terms of sharing their electrons. Okay, the orbitals of the two atoms actually overlap and they share. This happens to be an F2 molecule. It's got 7 valence electrons. They each need how many more to get to 8? 1. So they say, hey, let's team up and share each one of our individual ones. Okay, and so they share that. So now each atom has 8 electrons in their outer shell, which makes them happy, right? Okay, so they're sharing in that case. Okay, the other electrons that are out here, these right here, they belong just to that fluorine atom.
So it's like the Venn diagram, and what's in the middle is like what they have in common.
Kind of, yeah. Except they're not Venn diagrams, they're orbitals. But yeah, but it's kind of like that. That helps you remember it. That's a good point. Did y'all hear what he said? Okay, all right. So that's what covalent bonds look like. The problem with covalent bonds is some people don't share equally, do they? So we have two types of covalent bonds, sharing equally and sharing unequally, okay? The first kind is which are more common, are polar covalent molecules, okay? And that is when you have an uneven distribution of charge between the atom. In other words, one atom gets to have possession of the electron more than the other one, okay? And it's going to be the one that has the more electronegativity. Because remember, it's a tug of war. Whoever's got the higher electronegativity wins the battle, okay? And so the one that's more electronegative will get the electron more. These have an electronegativity difference of between 0.3 and 1.7, okay? The uneven distribution of electrons creates something that we call dipoles, okay? So those funny looking symbols are not S's, they're not H's, they're a sigma, okay? Greek letter. And what it means is it's slightly positive and slightly negative, okay? Huh? Okay. So the uneven distribution creates these dipoles. So what happens is hydrogen has a lower electronegativity. It doesn't get the electron very much. So it has a slightly positive side to it. So because the electron spends more time with the chlorine. Chlorine has a slightly negative, okay? They're called dipole moments, okay? And it has magnitude and direction. And we always draw it in the direction like this arrow from the positive, and the arrow or the vector goes towards the negative. The arrow goes towards the negative, okay? Which, when we get further into the unit, you'll need to know more about that. But this is just an overview. A nonpolar covalent shares them equally, okay? Anytime an atom is bonded to itself, in the case of our Brinkelhoffs, hydrogen, oxygen, it is a nonpolar because they have the same electronegativity, so what would their difference be? 0, right, okay? And so here's an example of hydrogen, and so it's sharing that electron equally, and so they're even Stevens, so to speak, okay? And it has an electronegativity difference of less than 0.3. So the vast majority of covalent compounds that we're going to talk about are going to be polar. However, a lot of your hydrocarbons, like gasoline and things like that, they are nonpolar. So that's not to say there's not a lot of nonpolar compounds. There is. We'll just tend to deal with polar more often. So electronegativity differences is how you actually truly define what kind of bond it is, okay? And quite frankly, most of the bonds aren't 100% one or the other, okay? But we used our electronegativity differences to truly determine what kind of bond it is, okay? And I have that listed on the bottom, or towards the bottom of your notes. But I wanted you to see this visual of what they would look like in terms of electron distribution, okay? So for nonpolar, it's going to be even, looks the same. For polar, it's going to be slightly, off kilter because the chlorine has a higher electronegativity, so it keeps the electron longer. And then, of course, ionic is the outright transfer of electrons, outright giving them away. Okay? So this is our electronegativity trend. Okay? Remember, it's highest at fluorine, because fluorine is the most electronegative, right? Okay, it always wins. Remember, I told you that the noble gases have a dash. They don't have a value. It wasn't entirely true because krypton, xenon, and radon do have one because they can participate in some bonding. It's just not very often, so we don't talk about them. So for our purposes, it's 0 because we're not going to deal with them in a compound. Okay. So if I was to figure out what kind of bond I had between, say, lithium and fluoride, I would look up their electronegativities, and I would say fluoride is 4.0, lithium if it's 1.0. So the difference in electronegativity is 3.0. So that would definitely be ionic. Okay? That would be an ionic bond between the two. Okay? Let's say I was going to look up, I can't read those on there. Let's say I want to do nitrogen and oxygen, a bond between nitrogen and oxygen. Oxygen is 2.5, nitrogen is 2.0, so the electronegativity difference would be 0.5, so that would be polar covalent. So that's how you do that, simple subtraction. Okay, you do not have to memorize the electronegativity chart. That would just be cruel and unusual punishment for you. I will either give you the values or I'll give you a chart and you can look them up. You don't have to memorize those. Okay. And that is where we're stopping today. I told you it was going to be short and sweet.